Yeah, you're ready?
Hello everyone. Today I'm going to talk about shooting and this is our output. And this is the problem. When we throw the rubber band with one side is tight and one side is not tight, and we can find that it will shoot, but the distance it shoot will be lower. And in this topic, we will focus on the first distance and the speed of the rubber. And of the phenomenon, we can see that the tension on both sides, when the tension at both sides of your rubber band is different, and it will cause rotation. And the rotation is only because it will be more stable, so it can fly farther. And the rotation also causes the rubber band to be effectively sliding. The rotation on the rubber band will cause friction, which will keep the rubber band stable. It will be when it's rotated, it will be stable. So the rubber band won't shake, so it can fly farther. And when the rubber band was rotating, it will cause the pressure on both sides different. So it will you will turn and through. If you throw it this way and really rotate, it will come to this. You will turn. And here is our method. We use this to shoot the rubber band, and we put the long place, and this one is to measure how it turns and how far it is. And our rubber band, we pull it to 11 feet cm, and the height is this. And the rubber band pull is clean, and the rest is not. And we can find that this one is log X, this is log L. The log L is the difference between we pull the rubber band this tight and this not tight. Is the difference, just like rubber band, and we pull the different L to pull this, and we can find that the difference between this is L, and the X is how we shoot the distance. And we can start it to get log, and we can find that the slope is 0.258 and so the more the non-uniformly stuck is, and the further the rubber band fly. So we make it into the figure, and we can find out that is the relationship between this is close to x equal to a times L power of 1/4 plus e, and to draw this line, and we can find that the L, the limited L is more near to L is 15 cm, and we can find that the X is about the 120 cm, and it is the minimum of the distance we found. And here is the is because the rubber band shoot and you will turn. So this figure is talking about what is turn. And we can find that we divided the x and what it turns the y, and we can find that the tangent theta that it turns. And we can know that it is the relationship of this, and we can find that the rubber band is the turn is very small, so we can ignore it. So this is our conclusion. The non-conformity state will keep the rubber band stable and fly farther. The rubber band restore when the rubber band is more than high speed will cause defect. And the relational experiment between L and x is x equal to a times L the 1 power of 1 by 4 plus 2. And the maximum distance we found is 140 cm. And the turn caused by rotation, we think that it can.
Okay, questions from the opponent.
Okay, thanks to for your report. So for the reporter, the opponent want to ask, do you think will the size of a rubber band affect the result of the experiment?
Yes.
Okay. How many times do you repeat your same experiment?
I repeat 3 times.
So do you have the error bar? And are you certain that your experimental setup between won't encounter any friction problem during the experiment? Are you certain that the friction between your setup and the rubber band won't affect your experimental results? Okay, thank you. I will move to the next question. And did you measure the air resistance? Since you used Bernoulli's principle, so did you analyze?
I didn't use the theory. Just I didn't.
Okay, thank you. Do you find the elastic boundary of the rubber band, which the rubber band can't reach anymore, and after the experiment it can reach?
I did.
Okay. After the rubber band is released, is it a projectile motion?
I didn't know it is, but
Is up.
that.
Preparation of the opponent.
Honorable juries and fellow competitors, I'm the opponent from Team Excelsior. Today I'm going to oppose problem number 4, shooting rubber band. This is the problem statement. A rubber band may fly a longer distance if it is non-uniformly stretched when shot. And if you give it a spin, and it will fly further. And the problem asks us to optimize the distance that the rubber band with spin can reach. And we'll mainly focus on investigating how spinning affects the distance that the rubber band can reach, and how do different parameters affect the distance of a rubber band. On the reported outline, in the theory part, we talk about the rotation and the pressure of the rubber band. And he also used the Bernoulli's principle to explain why the spinning rubber band will fly further, but I don't think it explained well. In the experiment and the analyzed part, it only talks about the elongation and didn't have any more parameters. And then in the error analysis, and it talked about the uniform and uniformly stretched rubber band. And this is the strong and weak points of the reporter. First, it explained the phenomena well and had detailed analysis on his data. However, he didn't mention about the release method, and didn't talk about the measurement of angular velocity, and he didn't consider any friction and air resistance in his theory. And he failed to come up with the best way to optimize the distance that the rubber band can reach, which is the most main purpose the problem asked us to do. And in the point to discuss, in the theory part, I want to discuss about the elastic constant and the non-uniformly stretched length. And energy part, I want to talk about the elastic potential energy of the rubber band. And force part, I want to talk about the friction and the air resistance. They may affect the distance at which rubber bands can reach. In the setup part, I want to discuss about the initial angle of the rubber band, and that may cause it to spin. And in the experiment part, I want to discuss about the measurement of air resistance constant, and several parameters such as radius, elongation, or initial angles that may influence the distance of a rubber band. And the deviation part, I want to discuss the interference with the setup in his reporter's report, and the difference in elasticity of a rubber band may influence the distance and the results. And also the stability of short distance, since he didn't have error bar. And this is all my presentation. Thank you.
Okay, move on to the discussion. For question for reporter, will the shape of a rubber band change during a flight if it is spinning?
Yes, it may be changed.
The opponent didn't agree with it, because the opponent thinks the rubber band when it's spinning, it will be a ring shape and fly more stable during a flight. Okay. And next question is why the shape of rubber band is more stable during a flight if the rubber band is spinning?
Because the
Okay, thank you.
Because I say the here it will, the rotating will then come back.
Okay, so next question that I want to ask is, you mentioned that in your experiment, a rubber band, if a rubber band is spinning and it may shift to the other side, like the right side or left side. And so, did you know the reason of this result?
I didn't use the theory to get the distance in the theory, but I used I used the experiment to know this distance, and I just but I can know.
Excuse me. I mean, did you know why the rubber band shift to the right side or the left side?
Because if it is rotating, and we just we
use the
think that,
projector.
okay. Mention that this rubber band is rolling at this side, and this side the air go here is very fast, and here is not that fast.
I want to answer which is the
Which side?
no, the rubber band is fly this way.
Yes.
Okay. You make it. You make continue.
Okay. So this side the pressure is low. So this side the pressure is bigger. So the bigger will come to this side.
The opponent agreed with you, but I think we can come up with a better explanation. Since the rubber band may, you say the pressure there is lower.
Yes.
So if a rubber band, the pressure, the air is come this way, and will fly. Did you agree that?
Yes.
Okay. So according to the Magnus effect, the opponent thinks that it's a spinning thing, spinning object, when it's flying, it may have the air there may be the pressure will be lower, and this side is bigger. So I think the Magnus effect is a good way to explain this phenomenon. Did you agree?
Yes.
And so, if a rubber band shifts to the right or left side, how did you consider its distance?
You say this distance.
Yes,
This or
this one.
because it's very small, right? Just we can do this, so we just get this one because it's very small.
Okay.
Thank you.
And so every rubber band has slightly different from each other. So how did you solve the problem of different rubber band have different elastic force?
I didn't do other rubber band. I just one track.
Did you use one same rubber band to do the experiment?
Yes.
So how can you make sure that your rubber band maintaining the same elastic force?
I can. Then but you will change that much.
The opponent didn't agree with you. The rubber band, if you stretch too many times or too many elongation, the rubber band may over its elastic boundaries, and the elastic force of a rubber band may change. So the better way, I think you can, how do you think you can improve this problem?
You can, I can just shoot, I want to see this, the force to make sure it is not.
Okay. So, do you think it's a spinning speed same every time when your rubber band on spinning to the same length? Like, you want to cause it spinning, you need to make this side have more like this one. So this one is stronger and this one is okay. So it's a spinning seat every time. Same every time when a rubber band is spinning, if it is in the same uniform degree.
It will be the same, but it will have like more higher or lower, so I do like many times.
Okay. So how do you think so if you conduct so how did you consider spin into your theory if since you don't have a theory of spin?
Yes. The theory of spin is more hard, so I didn't use the theory to calculate the spin speed.
So what? Next, I want to change the method. How do you? What basic knowledge do you think they will contain in the spinning theory?
What do you mean spinning theory?
You want to measure the distance in your theory, right? And so you want to get the distance of a spinning rubber band you make. You need to combine with some basic knowledge. And so how did you? What do you think it will include?
The rubber band is rotated, and if the rubber band want to come like this side or other side, you will obtain a little track this, and this spin will make.
Okay.
So if it is stable, it can very longer. And if it is not spin, it can just this shoot and.
Okay. Thank you. So you mean it included an angular velocity?
Yes.
And how about the error system part?
Because I didn't really calculate this in the theory, but our experiment is.
Okay, thank you. So I want to ask the last question. And did the rubber band obey the Hooke's law? Yes or no? No. Okay.
Because
Thank you.
I want to summarize the discussion.
So this is a discussion summary. First, the spinning rubber band shape is stable during the flight because it will cause because it's a stable ring shape, so it will easier to cut through the air and fly longer and less affected by the air resistance. And the second, the non-uniformly stretched rubber band gives it a spin which symbolize a flying contractile motion. And the air resistance of the reporter thinks that it is not important. However, the air resistance may affect very well. So that's why we need to spin the rubber band so it can fly further. So this is our discussion summary. Thank you.
Questions from the review. Can you put down your mask?
I want to ask.
Excuse me, can you put down your mask?
You think the Because we use non-uniform stretch. And you think the non-uniform stretch will let the flight path of the rubber band more accurate or inaccurate?
I think if it is spinning, its accuracy will increase because.
So you think it's accurate?
So it is accurate because.
Okay, thank you.
Okay.
Okay. And the second question is, how does spin affect the experiment result?
The spinning will obviously increase the flying distance, and you can observe the magnetic effect, which it might shift to the right hand side or the left hand side.
The spinning, when they spin and become the pressure differentials on the right hand.
Okay. And whether the uniformly one will also spin?
Pardon? Can you?
If we use uniformly stretch, it will also have spin.
No.
Okay. Yes or no? And which energy will turn into which energy the initial mechanical energy will turn into?
The
Kinetic energy, rotational energy, or deformation?
it will turn into the kinetic energy
I think opponents think the elastic potential energy will turn into kinetic energy, make a rubber band fly.
Okay. And did you think the launch angle will affect the experiment result?
yes, but
And which can let the rubber band have the biggest distance? And
the distance will be
I think it won't be the 55 degree because the air resistance and the launch height will affect. So I think it's between 15 degree to 30 degree.
I mean, the variation of the viewer. Okay, presentation.
My name is Bodley, and I'm the reviewer from TYPT. And today I'm going to review problem number 4, shooting rubber band. And in the when I'm focus on stretch amount and the relationship between distance and stretching distance. the rubber band. For their cons, they didn't calculate the air resistance and not accurate experimental methods. And for their data analysis, they have the log and distance. And for their cons, they didn't have the theoretical line and no comparison between the theory and experiment, and lack of the error bar. And this is overview of the opponent. And for their short caution, they ask the air resistance, elastic boundary, and size of the rubber band, and consider friction at the setup or not, and projectile motion. And for their pros is they consider the air resistance, which is important factor to affect the experiment results, and consider the elastic boundary of the rubber band, which will affect the experiment results. And for their cons is they lack discussion of the energy transformation. And for the discussion, they discuss the shape of the rubber band and the pressure difference, and the rubber band elongation and the Magnus effect. And for their pros is they ask critical questions about the flying process of the rubber band and point out the spinner of the rubber band haven't been considered in the reporter's theory. And for their cons is they lack discussion about the reporter's data about log L and log X. And the opponent asks, did you consider the air resistance? And reporter said no. But in our opinion, we think it needs to be considered because it will affect the rotation of the rubber band and will affect the distance that rubber band can reach. And they asked, did you consider the elastic boundary? And reporters say no. But in our opinion, we think that will influence the experiment results. And we asked, you think the 9-point stretch can let the rubber band fly pass more accurate or inaccurate? And we think it will let it more inaccurate because it will have the Magnus effect on it. And the opponent and reporter both say accurate. And we asked what energy do you think the initial magnetic energy will convert it into? And we think the kinetic energy and rotational energy and deformation. And the opponent think it's kinetic energy and rotational energy. And reporter think too. Thank you for your attention.
Thank you. Concluding remarks from the reporter.
It is our conclusion remark, and I want to talk about some things. First, we didn't just do the theory. So we should make more time of the experiment, just like some others rubber band to collectively take our point. And because we don't really calculate the speed, the angular the velocity of the rubber band, so we should calculate it. And what I want to say is about the air resistance, because we did not use the theory to calculate our data. We only use the experimental data to discrete. So the air resistance is just in the experiment. So I think I don't need to put the air resistance in our data. So it's my
Questions from the jury.
Could you please give an explanation why the time of flight will be longer for a spinning particle?
Because it's more stable. It won't like we shoot, and if we don't have the one type, one not type, and you will be rotate like shoot and rotate like this, and you will not that long. So if we shoot from one type and not type, you will rotate, and when it's stable, it can just like this and go far.
However, I disagree with the reporter, and we think that the time and the spinning rubber band or not spinning rubber band would be nearly the same, but it will a little bit affect, but it will not that much.
I agree with us because when the rubber band is non-uniformly, it will have speed, and if it spins, it will have angular momentum, and this will let the rubber band more stable, so it can fly more. Its time can be more long.
Any more questions? Yeah, Professor Chen.
Yeah, thanks. So could you bring your data again in your presentation?
Which data?
Yeah, this will be good. So the y-axis is the length of the traveling. Is that right?
The L or which one?
Your x.
The X is how long we shoot.
Yeah, the distance. So
Yes.
what's the number? Is like a
No, this we picked wrong. This is log L and this is log X.
yeah, so yeah, because it is very small. It's hard to
Yes.
read. But I remember that from your conclusion is like a 120 centimeter. That's the maximum traveling length. Is that right?
It's the maximum for this rubber band because the L is only equal to 15.
So my question is maybe for the reporter. Typically, when we stretch a rubber band, it travels quite a long distance. So why, in your experiment, it only can fly for 120 centimeter? What's the major reason it
Because
flies so short?
because our height, because the height we shoot is not very high, it's just very low. So it may be just like the gravity.
May I answer? May I answer about the
But the jury didn't ask you a question, unless you want to ask some questions. Yes. Okay. I also have a question for a reporter. Yeah. Have you really considered spinning effect when you only stretch the rubber band, right? But did you really observe the spinning of in some way, yeah, of the spinning?
Because it will spin. We have checked just you use the phone to make video, and we can make sure that it's spin, but we don't have the camera to let it to slow move that we can find the rolling speed.
Okay. A second question, yeah, related to the question from Professor Chen. So you only consider this height for shooting the rubber band, right?
Yes.
Only that a little bit more than 10 centimeter.
We use these things like maybe like this, and just put one thing on this, so it's nearly like this.
Okay, so that's why I mean it shows
Yes.
so short of the distance the rubber band travel.
Because here is not that long, so we can just it's very because the hole is not long. It's
Okay,
very short.
yeah, thank you.
Have a seat.
proceed.
Thank you.
Okay, so that's the score release from the jury. Okay, for the reporter, 4, 6, 4, 4, and 5. Eight, 7, 5, 6, and 7. For the reviewer, 8, 8, 5, 6, and 5. Okay, thank you. So we'll have another 15 minutes break.